the error becomes bigger and bigger. But when the robot sets a goal, we will consider this estimation of robot position with regard to the measurement to the goal. So the error becomes smaller and smaller. And finally, when the robot reaches the goal, the error between the robot position estimation of robot position and the ideal robot position converge in the end. And this figure shows the particle cloud representation for the robot position estimation with regard to two obstacles. And this figure shows still the particle cloud representation, but it's for with regard to the measurement with regard to the goal. This figure shows how particle filter works step by step. It will have a better illustration. Figure A shows the prediction of one step when the robot near obstacle O2. And after that, we obtain the weight for each particles based on the measurement from the robot to the obstacle O2. You can see the area of the particle means the weight of the particle. That means we can see some particles have a bigger weight. That means they have a bigger weight. A bigger area, they have a bigger weight. And after this step, we will do the resampling step. Resampling step, we will propagate the particle with higher weights. So that's why we see just the particle cloud becomes smaller. That is because the resampling step make a precise result. So we can see this figure C shows the resampling step. And after figure C, we will do the prediction of next robot step based on the system equation. This similar result is the same as the first one, but is regarding to escape a concave obstacle. We can see in the process time, in some period, we cannot obtain the estimation of the robot position. That is because in that period, the robot cannot sense the obstacle and the goal. So we do not have any measurement. Since we do not have any measurement, we cannot obtain the estimation of the robot positions. Still, when the robot gets close to the goal, the error between the estimated robot position and the ideal robot pose converge in the end. That's what we want, right? This figure shows the particle cloud representation for the robot navigation. And this figure is a particle cloud representation for estimation with regard to the goal. And still, the same thing. Figure 13 shows the illustration of how the particle filter works. We can see still the figure B, we have some particles with bigger area, and which means it's bigger weights, and we do the resampling, and we can see the particles with bigger weight exist, and the particle with smaller weights diminish, and that will give us precise results. And for figure D, we can see we just made a prediction of next robot moving step based on the system equation. Okay, here's our experiment result. For our experiment was implemented by using both MATLAB and LabVIEW. For LabVIEW, it was mainly utilized for obstacle avoidance using the velocity potential field method approach. And for MATLAB, it is used for obtaining the estimation of robot paths and obstacles based on the data, sensor data we collected in order to build a local map of visible part of the obstacles. So here is a snapshot of our experiment animations. In the beginning, the robot will go toward the goal, but there lies two obstacles in between its paths, and one is smaller, one is bigger. So when the robot gets close to the obstacles, it will choose the proper turning direction, turn left or turn right, based on the local map it has from the sensor data. Then when the robot bypass the obstacles, it will send the goal. Then it will have a measurement with regard to the goal. And after that, it will reach the goal. These two figures were obtained using MATLAB. We can see in figure 15, the estimated robot position and the ideal robot position converge when the robot went to the goal. And and figure 16 is a particle cloud representation of figure 15. We can see the area. Some particles have a bigger area, so that means they have a bigger weight in the navigation process. And there's the scenario 2, the same thing. And the robot successfully escaped the concave obstacle and finally reached the goal. And still, figure 18 is the estimation of robot position, which is shown in green square, and the estimation of 5 obstacles, which is shown in green asterisk. And still, finally, the estimated robot path and ideal robot path converge in the end. And the figure 19 is a particle cloud representation of figure 18. Conclusions. In our research, a switching controller for robot navigation without obstacle collision was successfully proposed, and the feasibility of it was verified in two typical scenarios. Both simulation and experimental results illustrate that through our proposed fast-line approach, robot path estimation regarding to the goal with known absolute position performs better than robot path estimation regarding to the obstacle with unknown absolute positions. And finally, when robot reached the goal, the estimated robot position and ideal robot position converge in the end. But the future work, we can consider all the measurement for each robot moving step. And more scenario could be tested, not only these two typical ones. And we can also take into consideration about moving obstacles or human avoidance. And the last future work could be improve and adjust our experiment.